thank you all for being here. It's on a Wednesday afternoon, right? It's a beautiful location here. Well, so I'm going to make a very pragmatic and utilitarian sort of presentation, not very philosophical. I won't talk much about values, which I'm guessing that we all share anyways. It will be more about basic skill sets that I think that we are required for advancing in the career, what the path will be for your careers. I'm speaking mostly to the PhD students. And I'll base all this on what I've learned from others, from my own personal experience, and some limited empirical analysis. So I think that we hope that our career paths and personal growth lead us through several stages in our career. And we know that we start off with some sort of apprenticeship, learning some sort of trade like engineering or architecture or some other, or construction management, that we do some exploration. Usually we end up doing research, or we get into various jobs in our 20s and 30s in transportation or all sorts of different places. But at some point we make a commitment to both an institution, like a university, to our students, to a particular professional community, and to a vocation, and we have to then stick with that for a while to make some sort of an impact. And at some point you emerge into or you take on some leadership responsibilities as well, department administration, professional society leadership, industry professional leadership, that sort of thing, journals, conference chairing, that sort of thing. And hopefully at some point in your career you eventually also evolve into taking some sort of stewardship as well, and that might involve membership on national panels of the national academies in the US, and in Canada it would be like the Royal Society. Or you get involved in endowing chairs and endowing other, or creating institutions that can sustain your profession. So those are the transformations we hope we go through. And I think one thing is that an early transformation is that we have to transform from being a student where we're externally validated to being internally motivated, setting our own goals and our own objectives and making sure that we achieve them. And not expecting the pat on the shoulder like we've been trained to expect for the first 30 years of our life. So that's a big transition too. So I know that when you're doing, so you're starting your career path, one of the big things is you have to acquire that basic skill set. And we all think of courses as being a critical part, conventional part of that skill set. However, I think that books are really useful in developing that basic skill set, because they introduce you to the archetypical people and situations that you're going to encounter in an academic life, because we're talking about construction, academic career path. And I thought I would just at least point out 6 books that I really have loved in my reading life. I really like The Masters. It's written by C.P. Snow, who wrote in the 50s, 60s, and 70s. I think he may have even started in he wrote the Strangers in the Masters series. And in particular, I like his book called The Masters. It's a book about an election of a master of a college at Cambridge, set in the 1930s with the war, the Second World War looming, and the Nazis looming. So it tracks really archetypical characters that you're going to meet through the rest of your career, and all the politics and so on that goes on, and the battles, the very passionate battles about who's going to become the master. Because when you're a master at a college at Cambridge, you're a master till you die. Okay. So that's an interesting book. I just read This Town by Mark Leibovich. So it's the New York Times called it a Confederacy of Lunches. They're making fun of the book Confederacy of Dunces. And it's just a fascinating book about politics in Washington. It's good for all of you in the US to be aware of how everything inside the Beltway works. But it also is interesting because I think a lot of that sort of stuff goes on in any career, and it's just interesting for you to read about that. Moo, written by Jane Smiley, is hilarious. It's a satire of life at a state college in the US. It's sort of this sprawling narrative of all these different characters, and it's really quite funny, and it really represents well a place like Texas where I was, or in Iowa, or maybe even a little bit of University of Michigan. Name of the Rose, Umberto Eco, why did I throw that in? Because it takes place in a monastery in the 1300s, and everybody knows that universities emerged from monasteries and places where, Cambridge and Oxford are 800 years old, University of Paris is almost 800 years old. So you see that the power of orthodoxy in one of those institutions 700 years ago, and you encounter orthodoxy in your career, in your university, even today, and you'll see how powerful that is and what sorts of problems that creates. The Rebel Angels is written by my favorite author, Robertson Davies, who's Canadian, and I love that because it's really Baroque and bizarre and takes place in an arts college. So it's not us, right? But it's, in an arts and humanities college, and some very interesting characters. And finally, A Tenured Professor by John Kenneth Galbraith. I love that one because he's a great economist. He's also from Ontario, but he was a chaired professor at Harvard for many years and a professor emeritus. And that is just funny. It's just a satire about economics. So, okay, so what other teaching skills? Oh, I should have been popping up those figures. I'm not used to, I am not a build slide person. There you go. Beautiful, aren't they? Yes, I should have had those up the whole time. Okay, I saw them in my mind's eye. Okay, so what is the other skill set that you need to acquire? Well, you need to acquire teaching skills, and at Waterloo we have the Center for Teaching Effectiveness, which is a very large organization. You can take courses, you can get certification. It's becoming more important in your career, more so than ever, to get formal teaching and pedagogy and so on. That's good. In the US, there's programs that the National Science Foundation runs where you go up to West Point and you get instructed for a week on teaching. Those are really good things. I'm not going to talk a lot about them today because that's basic stuff. You need to pick it up, and that's good. And then all these other skills that you see listed here, a lot of universities like Carnegie Mellon, Texas, Waterloo have seminar series that try to teach you some of these skills that used to be taught more in your apprenticeship type relationship with your advisor, but advisors are so busy and it's more efficient to convey this knowledge this way, and then also to help you pick it up and practice through your PhD career. So you got to learn how to review manuscripts, prepare funding proposals, do all those sorts of things, even research data management. We have a seminar on each of those at Waterloo, and I think Carnegie Mellon was doing that 25 years ago, so it's a good thing to do. Okay, so let's assume that you've gained the skill set, you've been to graduate school, you maybe worked in a few years in industry, you have maybe done a postdoc. What is the way that you develop your research program, which is generally how you're going to be recognized, at least early in your career? Well, one thing that you do is you begin to write lots of proposals based on partnerships with colleagues and, when you're young, senior faculty, because they have the reputation, they have the knowledge of what can be funded, and you have the energy, right? And some new skills. So you bring that to the table. You bring the skill set to the table that you learned in your courses, and you build on that domain knowledge through experience. And what I'm going to try to show is how that sort of works. It's almost a game of acquiring domain and tool knowledge and expanding your research program. So what I try to show is so this is going to become more and more full as we go through it. And I was telling you about using empirical data at some point. Here I'm using a case study. The case study is me, because that's the only case study I have really good data on. And the bottom is the skill set that I picked up mostly early in my career, but a couple of those skills added later in the career. And then the vertical axis are the domains that you acquire. You acquire domain knowledge as you become more experienced and as you do more and more research in more and more areas. So usually when you're starting as an assistant professor, you're starting with a hammer and you're looking for some nails. You're doing the opposite of what you're told you're supposed to do, but which is try to find a good research problem. But you have all these tools and you're just looking for a problem to hit them with, right? Or nails that you can hit with your hammer. My undergraduate education in systems design engineering gave me a background in control systems, graph theory, modeling, machine vision, design methodology, that sort of thing. And so those are the sorts of tools that I brought to the table. I had worked in construction as well, but that's kind of pretty craftsman and machine operator type knowledge, not management type knowledge. So the first thing that I did was I ended up as an undergraduate for my senior design project, which you do your last 2 years down there, applying machine vision for crack detection. And I used pattern recognition, machine vision. And I put this up almost as kind of, it's humorous in a way that to do machine vision, you had to have a digitizer and a frame buffer. And it was really great if you had a 250 by 250 resolution image. That was considered high resolution. So I applied some machine vision and got some good recognition, maybe 80–90% recognition. And the next 30 years, people have been working on this, including myself, and we haven't improved the recognition point much beyond that. It's a really much harder problem than it looks like. But then for my master's, I did almost the same thing. I applied Huff transform and machine vision to subsurface pipe mapping and so on. So just applying those basic tools I knew. So what do you decide to work on next? So I think, this is my theory, that we end up applying new tools to domain areas where we already clearly understand the problem, or we end up applying the tools and skills we already know to new domain areas. In my case, a lot of what I learned in undergrad and grad school got applied on my PhD, and I threw everything I knew at my PhD, everything except the kitchen sink. This is the whole PhD. This is 3 years of work right here. 2D and 3D image data analysis and fusion. So we had I was using laser scanner and 2D imaging device. Multi-layer quad tree model. We got data from many companies as well. Built a robotic pavement crack sealer. It didn't move. It's just that thing you see on the floor there, but that was version number 1. And even graph theory and artificial intelligence for path planning, for the most efficient path through the crack network. I just threw everything I had at this problem, and then I graduated. So I used all those tools on that one very narrow little problem. Okay, so I'm going to, but why do we do this? Because it helps us manage risk, right? We do this sort of building by tool or by domain because it helps us manage risk, and it allows us to bring something to the table in a collaboration with somebody else so that we can hopefully succeed or build a good, or be useful on a team. So that's the reason we have to go one way or the other. So I got to UT Austin at some point, got to be a professor there, and the first thing I was asked if I wanted to work on a new domain problem I knew nothing about, but it required 3D CAD and databases. So I thought, okay, I've got the tools, now I need to learn about this domain problem. I had a fantastic student named Walter Hornaday, and we went out and he did most of the work. But the first thing we did was we formalized the processes involved in heavy and critical lift planning and wrote a nice article about that. Then we started to try to automate some of the steps. And this is where I made one of the first really big and stupid mistakes that I've made so many in my career. I couldn't make a list long enough for you, but we spent at least a year trying to integrate 3D CAD with relational databases because we wanted to make parametric modeling possible in our lift planning. So really hard problem making those two pieces of software work together. Wrote up a nice journal article, and it had it soundly rejected because it was not a contribution to the body of knowledge. It wasn't science, it wasn't anything. It was just that we made two pieces of software work together. So that was a good lesson to learn, but I felt horrible for my graduate student, Kuo Liang Lin. However, he is very successful now, so he survived. And we moved on, and this is what he ended up doing that did get published among a couple other things, which was multiple heavy lifts optimization, and it was a sort of a very complex optimization problem and planning problem in 3D. So he ended up working on that. What did we do next? Well, I got invited by a senior colleague. I'm skipping lots of parts, but I'm just showing how you build stuff. So I had these tools in graph theory and RFID, tag locating and statistics, and signal processing, and got invited to work on a traffic problem, so by a transportation colleague. And the idea was that we would get data from the Texas Highway Department. They had a study corridor in San Antonio where they had given out 10,000 RFID tags to drivers. We had readers spaced along the corridor. We had inductive loop detectors on the ground. So we're getting link data and point data, which we were, so we got time series off of that. We did data fusion between those two things, and we were trying to do automated incident detection. It was a lot of fun. A lot of other people were working on that problem. We eventually made some contributions, which were almost immediately made moot by third generation phone technology with GPS. So that I don't know if you'd call it a mistake, but it was an interesting experience. So a lot of people worked very hard to make these very expensive sensing systems work, and a simpler solution came along almost as soon as we had designed some good algorithms. So it's not all sad stories. Okay, so in the 90s, I started getting heavily into construction robotics and started up a field systems and robotics laboratory at University of Texas at Austin with some colleagues in mechanical engineering and civil engineering. And this led, so the robotics and the machine vision led to some new application areas. And one of the things was we went through 4 generations of that robotic crack sealer to the point where I get ill when I think of the word robotic crack sealer. Too many all-nighters in the lab. Eventually we built one that we took around to 10 different states and demonstrated on their highways. This is the one we built, and I have a Korean student who's a professor in Korea now who's built generations 5 and 6. So it was a lot, we got into that. We did teleoperated clinker clearing using augmented reality with real-time obstacle avoidance and laser ranging for clinker modeling. Believe it or not, this was a much greater than $1 million project with 15 people working on it, and I believe we got 1 journal article out of it, maybe 1.5, I can't remember. So, big project. Robotic pipe manipulator. So we had a 22-ton rough terrain crane with a 5 degree of freedom hydraulic manipulator on it. We started off with 8 manual levers, and you got 2 hands, so it's really hard to have coordinated motion with 2 hands and 8 levers. So we went to an ergo stick, and finally we ended up at a space ball, which gives you 6 degrees of freedom. The inverse kinematics are complicated because there's non-unique solutions. You have to use heuristics. And we did some real-time control. Beautiful, elegant work, complex. It had a fatal flaw that the lift at full extension wasn't enough to make it useful to eliminate. So the idea is to eliminate rigging, right? To have positive control over angle and position instead of having to use a crane. Now, this is applied in pipe manipulators for pipe laying now. You'll see robotic pipe manipulators, but for our purpose, it didn't work. It was good science in some ways, but it didn't work. And we mounted it in the lab to do further refinements. We also did trenchless robots, tank spraying robots, aggregate scanning robots. And what did I learn from all that? It turns out that large-scale robotics design was fun, but it did not lead to many publications. So the publications to level of effort ratio was incredibly poor. So it was just a good lesson. And also the construction equipment manufacturers were really good at picking off the low-hanging fruit like stakeless earth moving that we were making some of the pioneering advances in. And the huge lab with the high pressure hydraulics and the high voltage electricity it had become quite a burden. It was quite frankly unsafe to have graduate students in that lab, given that we were programming robots and sometimes making mistakes and breaking things like steel cylinders. So I turned my attention to other endeavors. We started with safety and state estimation modeling because it was a natural extension of what we had been doing. And you can see people like Jochen Teitzer, who is one of my students in that area, continuing on with that work. So what we did was we threw convex hulls over site objects, and this allowed real-time minimum distance detection between each manipulator link and each convex hull, and that facilitates real-time obstacle avoidance as long as you also incorporate a simple dynamics model as well, right? Because it takes time to stop a big manipulator. So the idea was that if you had a live process environment where you had chlorine or something in the lines, or electrical lines or people walking by, that this would be a way of having the heavy equipment not incur into those areas in 3D. So that was fun, and some people like Chang-Won Kim have moved on from that. He's a professor in Korea now. So the sensing kind of got going, and I ended up doing more work in that area because, again, you kind of build on your strengths, right? So one of the things was we moved on to making algorithms and technology for locating materials. And the first thing we started off with at Texas was coming up with new algorithms. So I think the very first algorithms for locating RFID tags. And we did that originally using RFID tags that were on the materials. You have a reader with GPS associated with it. You're reading thousands of tags a second. You're walking around a site, and you gather all that information. Then you post-process the data. And when you do that, so this is showing an animation of the tag. So the reader could be on you, or it could be on a piece of equipment. And this is showing the reader reading a tag from 3 different locations. And we do constraint-based analysis, but we also ended up doing center of gravity and triangulation. And a lot of people now are working on this, right? It's a big area to try to locate tags in 2D and 3D, outdoors, indoors, all sorts of things, ultra-wideband. The idea is that you eventually are able to estimate, even though you could only read that tag in a 50-meter radius, you're eventually able to estimate where the tag is within a couple meters. And not only that, you can do it for thousands of tags and thousands of pieces of material. The great advantage is that it improves productivity. It's about an 8-to-1 improvement in productivity for searching for materials, but it's also a huge reduction in risk in loss of materials on a lot of sites where the materials get lost behind a shed or under snow. So now there's some commercial technologies and companies, including the ones that we worked with and who funded the research, that are marketing this now. It's pretty widely used. So this was kind of fun because a lot of stuff I've worked on over the years is not widely used. But this went from just concept to widely used and commercialized rather quickly. So what was next? Ended up moving up to Waterloo. I had some money because when you move, they give you money. And we bought lots of toys, including laser scanners. So we extended the automated modeling to productivity and performance analysis. And in the early, about 2005, 2006, we designed some algorithms where you could pull, if you had a 3D model and you had a laser scan of a building in progress, you could pull out the design components out of that point cloud. And we could do that for steel up in the high 90s recall rate, for concrete a little lower, but if we used a 4D model, we could get up into the high 90s for both steel and concrete, and for earned value even better. So for earned value, we could get 99 or 100% accuracy. This has a big assumption underneath it though, which is that you're building the stuff where you designed it to be built. And it turns out when we started applying this to plumbing, mechanical, electrical, and plumbing work, it didn't work as well because especially in building projects, often those things aren't built where they're designed to be. They're built centimeters off, or they're built literally way off, and you didn't get that updated design knowledge. So we ended up getting into automated modeling as well. And you know, people like Bertschua Kinsey at Carnegie Mellon are working on that. I think people here may be working on this too, but I'm not sure. I think Vineet may be a little bit, but yeah. So this is a pretty busy area, and all this is showing is if we take a laser scan of our lab, we can automatically find all of the cylindrical objects in that lab in 3D and connect them with elbows, and we can make a nice model of the HVAC and the piping. So if you can find stuff where it's supposed to be, and then know generally where to look for stuff that you can't find and model it automatically, you should be able to do percent built as designed, you should be able to do quality control, you should be able to do earned value tracking. Maybe the real value isn't in any of this, it's in automated site layout, but there's commercial technologies for that. It's all connected, and we're trying to work in all those areas. As you get further along in your career, you tend to sort of move more and more away from the technology, I think. And in our case, I got an opportunity to work with Paul Goodrum at University of Colorado and Carlos Caldas at University of Texas, and a whole lot of really great graduate students and industry team members on a CII research program that went for 6 years. One of the things that we did was we had an opportunity to analyze statistically CII's benchmarking and metrics database of literally thousands of projects worth of data, where we had level of practice implementation, we had project performance, and in the case of several hundred projects, we had productivity information. So what that allows you to do is it allows you to relate practice implementation levels to project productivity and project performance. That's what that left-hand graph is showing. And it was showing that some practices had incredible influence on labor productivity. And on the right-hand graph, it's showing that IT integration and implementation can, on average, improve productivity by about 50% if you compare low and high groups of implementation level of IT of projects. So the reason I thought this was exciting and it was a great opportunity was we just didn't have this knowledge before. We didn't have empirical data that showed that relationship before. So it was a real rare opportunity to dive into CII's database, and it's something that you can then cite later and say, I would like to use this IT on this project because research has shown that IT integration improves project productivity by 50%. That's pretty cool. So, you know, it's a sort of thing that you should hopefully can use in the future. As you get older, you get kind of crazy too sometimes, and I got invited into another project by some colleagues at Waterloo. I didn't really know about system dynamics, but I got invited into working on it. I know Professor Lee is an expert in the area, and as an undergrad I had taken systems of differential equations and modeling courses, but that was when you had to program all that stuff. System dynamics is nice, user-friendly software that you can use to model very complex systems. And we ended up using that with partners, local industrial and municipal partners, and with the national government funding to do strategic planning for self-financed water and wastewater utilities. It turns out more and more around the world, you're having to self-finance these sorts of things over, say, 100 years, do it sustainably. And you're looking at all these complex relationships with price elasticity and pipe degradation and all sorts of things and how they interrelate in budgeting and finance. And you really want to come up with sustainable strategies. So this is how we're getting into that sort of thing as well. And then so I've got some domain knowledge. I'm safe that I can try to learn something new about process. And we did a lot of research around process. And so electronic product and process management systems, where you've got a workflow engine, you've got database management systems, document management systems, document markup systems, the internet, and you're managing multinational projects or projects dispersed, and you're trying to manage all of these processes and workflows, and this is what Samin and June and Dr. Lee and I are working on. One of the projects in this area is interface management, but other projects are things like supply chain management, change order management, and looking at a new idea that we're working on, which is industry foundation processes as a way of integrating all of the functions of project management, also as a way of enforcing compliance with best practices, thereby making sure that that thing that you saw on the previous slide, making sure that we get that improved project performance because we're enforcing those best practices with automated workflow-driven processes. So we're trying to develop all the theory, but also empirically support that. So it's just one meandering path through all that, and you see that the general transition is from technical issues to organizational and management issues. And I think that's because, for one reason, you've got to, as you get further along in your career, you have a greater appreciation for the impact of process and human behavior. Or some of us who are a little simplistic and technical make that progression. Some people start off with an appreciation of it. But also, functional technical knowledge is really difficult to maintain. And management knowledge is something that you sort of gain. So it's a sort of a natural transition I've seen a lot of colleagues make over the years, and you may yourself make that transition as well. So that said, what can we draw? What conclusions can we draw from all that? What observations? So that was 70 funded research projects, 100 graduate students. And what did I learn? And 500 business trips. A lot of mistakes. Well, okay, one thing I learned was that there's always this argument of quantity versus quality. This is a silly argument. We need both. So we're trying to go diagonal. So I learned that. That's good. I learned that when we write NSF and NSERC proposals, we need to think about impact, the impact that our research might have, and its intellectual content. And weirdly enough, even for industry work, which I do a lot of now, I think we also need to have the same two concerns in mind when we write a proposal, because otherwise they will just hire a consultant. So we always have to think about intellectual content and impact of our work. And then for our own academic career goals, this is where I'm going to get a little more controversial maybe, is that we don't just want to have an impact on science through graduation of students, through citations, through new theory, but we also want to have an impact on practice, on design codes, on what people and companies do in practice. And I think, I believe that that's important, that we want both if we're going to have an impact and progress in our career. So, how do we achieve impact in science? Well, we did a little study where we looked at 350 or so articles in construction productivity research over the last 30 years. That's correct, 30 years. And we looked at various ways of validating that work. So we just focused on validation, and then we looked at different categories of productivity research. And one of the things that people have done to try to improve productivity is constructability. We looked at where clear validation had been done. In the case of constructability, that tends to be functional demonstrations or case studies as opposed to empirical data collection or experimental studies. And in that case, definitely still clear validation tends to win out over time in terms of total citations, right? So we're looking at the older the paper, the higher the citation it should have, and the better the validation method, the steeper the curve should be. So clear validation wins out, but not very obviously over more fuzzy validation. And in terms of factors, though, where we're looking at things like impact of weather, shift schedule, congestion, and so on productivity, where we can conduct really controlled, empirical type experimental work, then you see that where you have done that well, you can have a huge impact. Not only that, if you look at the scale here on the vertical axis, where you have clear validation, where you've had empirical validation, you tend to have a lot bigger impact over time. So this scale on the vertical axis is about 3 times the previous slide, right? So to me that's interesting, but the question is, why am I focusing on citations? Why do citations matter? The physicists will argue that that's the only thing that matters, what other physicists think. And I think I would argue that there's some other things that matter. And so I borrowed a slide from Steve Thomas and Jung-Yi Song, who work for CII, the Construction Industry Institute, 130 member companies, 6 or 7 or 8 new research projects a year. So they've done, I believe, at least 100 research projects over the years. You do that right, 30 times. No. 200 or 300 research projects over the years. So we're on 302, so that's 300 research projects. It didn't start the numbering correctly, but it's almost 300. And what this slide does, it's really busy. It's kind of horrible in a way, but what it's showing is the perception of academics and industry on what was an implementation success in terms of area research, and what would they say has inherent higher value. And there's good correlation between those things, so that's good. And also what CII calls best practices, those blue things are in the high category, so that's good, right? So this is showing some, and you can track all sorts of different research areas that you may have worked on over the years when you look at that slide. It's kind of interesting. So in some cases, though, especially in the technology cases, it's CII research about these technologies. It's not CII research toward development of these technologies. So that's a fine distinction when you're looking at some of the stuff in the bottom left corner that would be a little bit depressing otherwise. Keep that in mind. Okay, so what this is showing is the research areas that both academics and industry agree are high implementation successes and high value, and it would be things like safety, change management, constructability, what they both agree by just opinion as low value and low impact would be things like technology innovation, automation. Again, let me remind you that that's studies of these things, not studies in terms of developing these things. And then there's some stuff in the middle there. And I'm skipping past this part because Steve presented this at our ISARC conference, and he was being challenging, which it was lovely. It was good. It raised some really interesting issues. So this one is interesting because it's the difference now. So the previous one integrated the opinions. This one is industry's opinion on the horizontal axis and academics' opinion on the vertical axis. And it's showing, I think this is sort of funny, that the R squared is very low. So the industry opinion of what was high impact, high value, and the academic opinion are very different. It's very interesting. So it's I find it interesting. Okay, and again, he's just showing some of the automation stuff. This particular one I like because this is showing product downloads versus citation counts, and I love it because it's not opinion, it's hard metrics. They may not mean anything, but they're hard numbers. So on the horizontal axis, we have product sales. So in each research area of CII, they have products, research products, like tools that you can download from their website. So for example, down on the right hand there, modularization. I worked on a tool that's been downloaded thousands of times, a PPMOF tool. So it's down there, it's high on the horizontal axis, but it's incredibly low on the citation axis. So the article that we wrote on the basis of that research, which has been downloaded by industry, the tool's been downloaded thousands of times. The article, up until a few years ago, was cited like 2 times. That was with Bob Tatum and Jorge Venegas were co-authors on that. And the vertical axis is the citation counts. Remember I was showing in the previous slides citations over time, and it's just really interesting to see what ends up high citation, low industry use, high industry use, low citation, and then some of the stuff in the top right corner, which is probably your dream, right? If you want to have impact in an academic career in construction, your dream would be to be in the top right, up there in the very far corner. Okay, so that's something you can look at later. It's really great to be in the top right. Information integration, I kind of like the fact that that was up there because our empirical analysis showed that it had impact, and it's becoming important. Okay, I just wanted to throw that. You've got the slides. You can look at them afterwards. I know that was way too busy, but it's kind of fun to look at it. So what are the career models? So I've described some goals and a particular meandering path toward those goals that I experienced. So I wanted to talk about what career models I've observed, and because these get discussed in grad school. They get discussed when you're a young professor, right? So there's the narrow, relentless focus, and you become the world expert on tiddlywinks, right? And nobody is more expert than you on that little narrow area, and that is a way to have impact. Now, that I'm exaggerating that because there's people who have had impact, huge impact in their careers, just real contributed value to society. One example would be Professor Hinsey in safety, who recently passed away. He always worked in safety. He did the work in safety, and he's had a huge impact in safety. So he would be that narrow, relentless focus model. Periodic strategic rebirth. What do I mean by that? Well, not a meandering, wasteful path like I took, but a strategic and thoughtful transition from one area to another and having great success in each area. And my best model of that is one of my mentors, Professor Hendrickson at Carnegie Mellon, who was my PhD advisor. He went from transportation to construction to environmental to back to transportation, and each stage wrote textbooks and highly cited articles, and is a member of the National Academy because he had a huge impact and was very focused at every time he did that. And I think the large and varied portfolio of research, that's where you're all over, but it's because maybe you're a Renaissance woman or man and you've just got interest areas all over and you're creative and you can have an impact that way if that's your personality, if that fits you. And my example of that would be my other major mentor. One of my others is Dr. Richard Tucker at Carnegie Mellon, who started up CII. And he, if you look at his work, was all over the place. He's also a member of the National Academy of Engineering. So there's no model, no specific model that works. There's a little bit of a debate around whether you should stay focused in the center or work on the boundaries between disciplines. So it's more, there's more opportunity, there's more innovation on the boundaries. It's more dangerous on the boundaries because you can get in over your head. That's where there's some debate, and I don't know what the answer is. The previous three, I think they're all valid. So I'm actually going to finish pretty quickly here. So success factors. So assuming you take one of those meandering paths toward those goals that we all generally agree on about impact and legacy, and you have one of these models that you're using as a basic strategic model or way of doing all of this, what are the success factors? And I'm just proposing these as success factors based on my experience and observations. I think the people who have high character, I see them do well over their careers. It really, it's amazing how the people who are reliable, who don't talk about their colleagues behind their backs, who are honest, who are hardworking, those people end up really, truly having success. I think that it's absolutely true that if you get lucky, you get involved in a hot area early in your career with lots of money, you get connected to the right people, absolutely early luck and momentum help in your career. And the fellow who wrote The Tipping Point, what was his name, proved that as well, right? So ethics are critical. and I have to teach a course in ethics at Waterloo, or a seminar. I believe that we all know what they are, we're all trying to be ethical, and we all make lapses. And we just realize that nobody's perfect. Correlating factors, I looked at all things, all my friends over the years, over the last 30 years, who's been successful, all my graduate students who are professors now, who's successful, or they're in industry. It's not the smartest ones. It's not a lot of things you'd think it is. It's, to me, the only correlating factor I can identify is hard work. It's the hardest working ones. It's the ones who collaborated, who are really good communicators, who built the skills, did some networking, and at the bottom of the list is analytical power, in my opinion. It's important, but we kind of have to assume we all have it. So that would be my observation. So a few minutes on common mistakes. I only put these here because somebody told me it's really important to have a resume of all your mistakes in life, that you learn more from that than your resume of all your successes, like all your articles and awards and so on. So to me, the one I keep making is failing. So Donald Rumsfeld said sometimes, the dangerous thing is not knowing what you don't know. And that's got me into so much trouble over the years, just not knowing what I don't know. There's some areas where I know I don't know anything about that tool, and then you get into an area and you don't even know what you don't know. And that's where you get in trouble. And I don't know how to avoid that, except go one tool at a time, one domain at a time, that kind of thing. And really be open to other people helping you and working with other people. So design versus knowledge discovery. I spent at least a good chunk of my life doing design problems, and you don't publish those. And often, and if you're not entrepreneurial and you don't make money by starting a business, that's not a really great way to advance your academic career. So don't build robots. It may be fun if you like to stay in the lab all night for days on end, and you like to have a lot of stress. Oh, I'm sorry, who's doing robots? I'm so sorry.
We have a several students
Okay.
who are working on building the robot.
I feel your pain, okay? It's good experience. Okay, it's good experience, yes. Okay, I didn't say this. But, so design, fun. Try to find some fundamental knowledge in that design experience. Try to pull out of it, what was the meta knowledge? What was the thing that you learned from that that's common to all robots or common to all construction applications? Don't get caught up in the design itself. Drawing general observations from narrowly focused data. The only reason I raise that is because I worked very hard on some projects over the years that I didn't even get published because the data was very narrow. Bridge scour on certain types of bridges and certain rivers in Texas. Not a good journal article. So try to figure out how to generalize your observations. Failing to communicate and share knowledge. I'm trying to think of that one, but you've got to get out there. You've got to go to meetings. You've got to communicate. You've got to share knowledge with your colleagues. Don't covet the knowledge. Don't squirrel it away. Just share it. Share everything. It'll work out better for you. So not writing down what you learned. This is kind of nutty because I've learned how to run good. I've been through literally, I think, hundreds of PhD exams, and I know how you prepare for a PhD exam. And recently, I failed to do what I know you need to do, and I had a couple PhD exams that didn't go so well for my students, and I think that's crazy. How come I didn't write down a list of what you need to do to prepare for a PhD exam to be successful? So write it down. Don't be lazy. So that gets around to some more of my mistakes. I've got a lot. These are whole categories. Avoiding hard truths. You're stressed out. You're running a bunch of graduate students, research projects, courses, and you're just kind of putting in the back of your mind the fact that all your money runs out in a year. Oh, well, if it's running out in a year, you should have had those proposals written today, because it's going to take that long for them to be reviewed, for the money to come in, to keep the flow going. And so it's really, in a lot of parts of your research career, it's really easy to avoid the hard truths. And if you're very rigorously honest with yourself and logical, you'll face them head on and work on those things first, the things that really matter. And don't get yourself in trouble. Don't dip and have to come up again, which, again, I've done. Engaging in office politics versus service, especially as you get into that leadership phase of your career, you'll mistake office politics for leadership. And leadership is leading by example and character and doing the right things and making contributions. It's not about being in charge of something or winning a battle. That's not leadership, that's politics. Now, there's a good part of politics, which is negotiating, communicating, and so on. But what I mean is the bad part of politics. Don't get sucked into that. It's stay away from it as much as you can. Keep it in mind you have to serve and you have to lead. Data collection. You can tell I love to design, I love art. I'm sloppy sometimes when it comes to data collection and laboratory protocol. And if you're not sloppy, that's wonderful, but if you are, you should recognize it and realize that data collection, laboratory protocol, experimental constructs are very important, and you have to be very careful about that. And all those things were all about getting cocky, getting sloppy. And the last mistake, I think, is, I had to add that one, is making a common mistake more than once. So it's sort of recursion in software, right? So you make a mistake and then you make the same mistake. That's a mistake. So try not to do that. Okay, so the last three, we're really closing in quick here on the end. So all that said, you learned all those things. You're trying to avoid those mistakes, keeping in mind what your goals are. How do you stay fresh? And I had this discussion with Dr. Lee because I think, even though I've been doing research for 30 years, I plan to be around for another 20 or 30 maybe. You never know. My father's 80 years old and still doing research, so give me another 28 at least. So how do you stay fresh? How do you renew? How do you keep going? And then what is the role of mentors in that whole process? What's your role as a mentor? And then I got something else I need to say at the end. So renewal and sustainability. Well, there's this issue of doing the things you know how to do. You do it because you become efficient. So that's smart. But if you keep doing those things, you're stuck in your comfort zone and you're not challenging yourself. And you have to challenge yourself. You have to accept that you're going to fail occasionally. So you have to find that balance between efficiency of doing the same things over and over again and busting out of the comfort zone, doing things that are scary, doing things that are dangerous. That's the only way you can keep renewing yourself, like learning Prezi. Okay, that was a joke, but okay. Skunk Works. This is my favorite because of the 2 or 3 areas of research that are most cited that I've worked on, they've all come out of stuff that wasn't funded. I call it the Skunk Works because I read a book years ago that called those the Skunk Works or the Black Ops. It's the back room, the stuff you do with no money. You got this great idea, you convince some poor graduate student who will be happy in the end that they should work on this. It's a really good idea, and you do it, and that's what generates the new research areas. So that RFID tag locating, that began with no funding, with just some cheap experiments up at the Ferguson labs. And so that's Professor Song who did that work, and that's been highly cited. He got highly cited based on that work. His thesis, well, it ended up being his thesis, but what started as his thesis is less, is less cited. So skunk works are important. It's all right you got to invest a certain amount of your portfolio of energy and research and money into high risk, high return, weird research. You got to meet people in other disciplines. Go to the architecture school. Go to the English department. Get out of the engineering campus. You just get out and read stuff in other areas. Go meet people in other areas because you just, you start drinking the Kool-Aid here. Go to workshops. One of the better ideas I had was at an NSF workshop that was multidisciplinary up at Lake Tahoe. It was fun. And it was beautiful, and it gave me tons of ideas. So go to those little small workshops. Those are great if you get invited. You know, we don't always get invited. Industry problems. I love industry problems. I absolutely love them because I don't really know what to work on. I talk with industry, and they say, this is a huge problem. We can't find the materials. Or this is a huge problem. We can't control. We can't manage interfaces, right? We need help. And you start working on those, and at first it seems straightforward, and you get into it and you realize there's all sorts of fundamental problems. I could do some really good fundamental research here. It's not just problem solving for industry. It opens your mind up to fundamental problems. I also think that you need to follow your students. That's a good way to stay fresh. I don't have the energy to discover new things anymore, social networking sites. I don't have the time. So I follow my students. They sell me on something. Dr. Haas, you should be learning this tool because we're a little embarrassed about you. Or it would be really good for you to learn this. And so, that's good. Listen to them, right? And then in theory, I think that a sabbatical would be really great. I've only had one in my life, and I totally blew it. I stayed in town. I kept up all my activities and didn't do a very good job at it. But I know people who've taken sabbaticals, and they claim that it's a great way to refresh and to recharge. So that's a good approach. Mentorship, I'm down to the last two slides here, I think, as I recall. I always hear about, and we have faculty meetings all the time about how we're going to figure out how to assign mentors to new young professors. And I think it's so artificial. It's like assigning husbands and wives, randomly. It's just, you can't make love happen that way. But so I think that you as a young professor, as a PhD student, you go out and you find mentors. And the mentor should be having the doors open, and you make a relationship. And don't just choose one mentor. Always have 3, 4, or 5 mentors. These are people who you admire, who you respect, who will give you honest feedback. Cultivate mentors. And then watch and learn them, and then be loyal. They're helping you. They're getting you on your first contract. They're teaching you things. They deserve your loyalty for the rest of your life. So that's critical. Don't climb that ladder and dump them, right? Okay. And then try to do the same thing in reverse. Because you'll never be able to give back to your mentor what they gave to you, so you just got to pass it on, and they know that. And good mentors are real good with that. They know that. So somebody nominates you for an award, you don't need to nominate them back. Nominate somebody else for an award. Pass it on. So the career stages. How did I get to here? Well, we're all trying to get through these stages. We're all trying to stay fresh. We're all trying to have an impact. And we don't do it by ourselves. We don't do it in a vacuum. In fact, we're just literally a player in this giant dialogue, this giant play. We're hopefully supported by our families and support them. Colleagues, you can't do anything without your colleagues. I couldn't have done my PhD without my colleagues. I didn't know how to solve the problems. I literally didn't know how to do stuff. And I needed my fellow graduate students to get me through. It's the same thing all the way through. Your students, these are all people that you're working in this. So that stuff I put up there, that is 90-something, 90, on the high 90s numbers of graduate students, a ton of colleagues. Those are just examples, and I was part of that. You certainly have a contribution, but just realize you're part of that. And I have to thank Behruz Golsapar because he did most of the work on this presentation. He did most of the slides, and he did the beautiful artwork. And I really wanted to thank him because he would get no thanks otherwise. So, okay, thank you. I think I'll leave to you.
Tishman legacy will be passed on to all of you and all the future students in this program. Thank you for having me here, and thank you for making time this afternoon to be with me.